Okay, thank you for joining this session here. This is a talk we recently delivered at the Strata conference in San Jose, and the topic of this talk is data reflections, making data fast and easy to use without making copies. So let's dive right into this. My name is Tomer. I'm the co-founder and CEO of Dremio, and Jacques Nadeau is the co-founder and CTO of the company. He's also the PMC chair of Apache Arrow, which is a columnar in-memory technology that is now in use by many different open source and commercial technologies. It's the foundation for projects like Pandas and various GPU databases. Projects like Spark use it, and so forth. So let's get started here. This is kind of what our world looks like today. We have a lot of raw data in many different places, and that includes things like operational databases. These would be the Oracle, the SQL Server, um, basically lots of different systems in which applications are creating data. And then there are also many applications these days where our data is stored. And so these can be SaaS applications like Salesforce and NetSuite and hundreds of others. Um, and so, in order to make this data available, what we've traditionally done as an industry is we deploy something like a data warehouse where we're copying data from all these different places into a single kind of clean, well organized schema in a data warehouse. And those are typically relational databases. The data warehouse itself is not something that can be used by every single project in the organization. And so what typically happens is for every project there are different needs, or every user has a slightly different need for the data. And so that's kind of why we have data marts, right? We copy data from the data warehouse into various data marts in different departments or different groups, and the data marts offer kind of a slightly different view of that data. Um, and then querying the data mart's often not fast enough. So what ends up happening in most organizations is that you then see different users creating BI extracts where they're extracting data into various BI servers, and often in an effort to accelerate queries, or at least queries that are known in advance for kind of reports, we create cubes. Often you see users downloading data into kind of flat files, into spreadsheets or CSV files, and maybe sharing those in emails. We see data being aggregated in advance in aggregation tables. That's either in the data mart or in a different system. And then finally, that data is kind of available for that analysis. But the result of all this is that we have now dozens of copies of data in the organization. It's just this giant mess. And so, I'd say about 10 years ago, we started seeing kind of the concept of the data lake, initially with Hadoop, and now we see that a lot with cloud storage like S3 um, and things like Azure Data Lake Store. And so basically what this looks like is data gets copied into kind of a landing zone, into one of these data lakes, which is a very scalable distributed file system, very inexpensive. It's very easy to get data into that data lake because there are no requirements to create kind of the schema in advance. And then often data gets extracted from the lake into a data warehouse, maybe the last 30 days or some aggregate level data, so that people can query it more efficiently. The problem is that this data lake really made the problem of data copies even worse. So now, instead of actually making it simpler and more streamlined, we see lots and lots of copies being created inside of that data lake. So we have kind of these ELT processes that are running in that data lake. We have tools like data prep tools that make it even easier to create copies. So now maybe an even broader set of users in the organization can create copies of data. Of course, we have tools to create cubes inside of the data lake, and we have various kind of distributed processing frameworks like Spark, and prior to that, MapReduce, that were all about creating more and more and more copies of data. And so this creates a big challenge for organizations. The challenges range from, of course, the obvious, just the cost and complexity of managing all these different copies of data. That includes storage costs, the disk space, and so forth. But it also means that it's very hard to maintain kind of the security and governance of this data. Now you have potentially sensitive data that's being copied all over the place, whether that's in the data lake or in all these external tools, floating around in emails, and basically IT kind of loses control of the organization's data when there are dozens of copies of data inside the company. And so that's a big problem. Uh, well, really, you might be asking, well, why is this happening? Why isn't it possible for us to just avoid this and maybe define some rules that would prevent people from copying? Well, it turns out there are actually good reasons that cause this to happen. Well, first of all, there are individual preferences and needs. So different users have different requirements and different needs. One user needs to join the data in the data warehouse or the data lake with their own private data. Maybe they need to look at the data with more business-friendly column names, or they need to look at a subset of the data. So every user has their own preferences and requirements when they're doing their analysis. And they also need to be able to blend it with their personal data. So imagine somebody who's looking at a very large data set of all the transactions in the company, and they really only want to look at the ones corresponding to their own accounts, the accounts that they manage. So they could bring in their own spreadsheet and join it with the broader data set that's available, right? And so that's an example of blending with your own personal data sets. Most users do not want to wait weeks and months for IT to make changes, and so we see this kind of notion of shadow analytics, where users, rather than waiting for IT to make the necessary changes and to prioritize those requests, they do whatever they can to kind of work around the system. And so that's why they download data into spreadsheets, or they deploy kind of an external BI tool to do whatever they can. Of course, all sorts of limitations around scalability and so forth. But maybe that's better than waiting so much time in their mind. And then the other thing here is performance requirements, right? So what we see is that when data volumes get really big, sometimes data has to be organized in ways that make it more efficient for querying. And so that can be everything from pre-aggregating the data so that we're only looking at session level data instead of the raw data, and that means that queries can be much faster on that kind of data. Or maybe it's looking at different subsets of the data, different partitions of the data, as opposed to the whole data set. But all these reasons are really legitimate reasons for wanting to create these duplications or these copies of data in the company. And I'll say, just to summarize this, what I consider the golden rule of analytics is that a single gold copy of the data is never enough to meet the needs of data consumers. So every time there's an attempt to create kind of a gold or a master copy of the data in kind of a clean, organized data warehouse, that really, that's a good thing to have, but it's never the end game, right? The users, it's never a situation in a company where all the users are just happy with that one golden copy and that meets all their needs. And so no matter what you try to do, people are always going to want to kind of massage the data and create new flavors of it, new perspectives on it. And so what's the solution to this? Well, we believe that because there's no way around those needs that the user have, that's just the reality of the world we live in, there has to be a logical world to enable kind of that flexibility to curate and to look at different perspectives of the data without creating copies. We call these virtual data sets. And so that's kind of we believe that is the solution to this problem, is give users the ability to transform and copy data in a logical way without physically creating copies of that data. And so what does that mean? Well, it's really these virtual data sets are effectively very similar to database views, but really designed for the data consumer. So somebody who's like an analyst and don't have kind of that technical skill. They're not a DBA. They may not know how to write code or even write SQL. These virtual data sets can include data from multiple sources, so they're not limited to being defined on a single source of data. You could have a virtual data set that joins data from maybe your S3 bucket or your Hadoop cluster, and maybe a table you have in Oracle, and then a personal spreadsheet. So that's an example of a single virtual data set that's just a join across all those things. It's important for users to be able to curate new data sets using virtual data sets. So that they don't have to copy data. So when the data is not clean, or it's not in the format that the user expects, or doesn't have the right column names, the user can make all those changes on their own without having to create a copy of the data, without having to export data into a spreadsheet. And then collaboration and security are critical ingredients here. So collaboration, this has to be as easy as using something like Google Docs, where you can create a new data set, share it with your colleagues, they can build on top of each other. And then, of course, collaboration and security are basically two things that go hand in hand, right? So the ability to decide who is allowed to see this data set and control that. And one of the really important things here is if we create a system like this where users can operate in that logical world and do whatever they want, but the system understands what they're doing. So they're not downloading data into an external spreadsheet and sending that in an email, but instead doing things through kind of an IT governed system. That provides a whole different kind of level of security and governance compared to the world that we live in today, where everybody's creating copies of data. And so the next question is, well, okay, that's great. We have this logical world. Anybody can do anything with data, and we're not paying any price. There are no physical copies. There are no risks that come with kind of physical copies, right? So on the left here, you see kind of the world prior to this approach, where everything was a physical copy. Every time we wanted to look at a different perspective on the data, we had to copy and ETL that data. And with this new approach, the data consumers here at the top are able to operate in a logical world where the relationship between data sets are entirely logical. They're just defined kind of based on relational algebra. Well, how do we leverage, how do we still provide the performance that people expect when everything that's being done is done at the logical level? And for that purpose, we kind of think about caching and various data structures that allow us to do that, and having a system that can automatically handle the physical world while users only have to worry about the logical world. And so we talk about the notion of a relational cache, basically maintaining different data structures behind the scenes that can help us achieve the performance that users want without users having to worry about copying the data. And so let's talk a little bit more about that relational cache now, something that we call data reflections. And before we start, just a quick kind of relational algebra refresher. So when we talk about kind of relational algebra and working with data, there are a few concepts that you'll hear kind of again and again. So the first one is relation, and a relation is basically a table, right? It's a set of rows. Each row has a fixed number of columns, and so that's kind of what a relational is. And then we have operators, and operators are really designed to do some kind of transformation on a relation. So the first operator is the scan operator that can scan the data from wherever it is. Then we have the project operator, which can kind of restrict the columns that we're looking at. We have the filter operator, which can restrict the number of rows that we're looking at, and then operators such as aggregations and joins. Properties, those are traits of data at a particular relation. So data can be sorted by a specific attribute. So it can be sorted by X, or it can be hash distributed by Y. Those are X and Y are examples of properties. We have various rules, and so these rules allow us to basically look at different combinations of operators and say that those are equivalent. So we can have these rules that can transform, let's say, a project followed by a filter to the filter followed by the project. Those two things are equivalent, and so the rules basically define these kind of equivalence, these equality conditions. Another example here is a scan, for example, doesn't have to project columns that aren't used later on in the execution graph. And then finally, we have a graph, which is a collection of operators structured in some specific order, and some kind of chained together in a specific way, and that defines a data set. So the basic concept behind the relational cache is actually very simple. Basically, what we're doing is we're maintaining derived data that is between what the user wants and what the raw data is, right? So rather than going in and scanning the raw data for every single query, we're maintaining some materialization of data that is closer to what the user, the answer that the user wants, but is not the raw data, right? And it's also not the answer that the user wants. And so the goal here is to really shorten the distance to data, what we call the DTD. And so you can see in this picture here, we have the original distance to data, which is the distance between what you want, what the what the query is and the answer for that query, and what the raw data is. And so that's what we call the distance to data. And by having one of these materializations, we call them reflections, that can actually reduce the distance to data, right? It can be something that's closer to what the user wants, and therefore when a query comes in, rather than going through the raw data again, maybe there's already some pre-processing that's been done at that level. Now these reflections can be basically any they can be anything, any materialization of data. They have to be, of course, derived from the raw data, but they can be derived with any arbitrary kind of operator DAG. They can be some kind of relational algebra performed on the raw data. Here's another example here. It doesn't have to be that trivial of a relationship. So in this case, we have two reflections that have been created based on the raw data. And you can see here one of the questions that the one on the top right here can be answered by looking at or can be constructed by looking at both the reflection, the second reflection, as well as the raw data. And that may be cheaper than going against just the raw data, right? So this is an example where and you see several examples here where answering a specific query, the what you want boxes at the top, requires data from more than a single reflection, as we saw earlier. Now this may seem okay, unique or interesting, but the reality is you're already doing this today. You're just doing it manually, right? And so if you think about how you're materializing data today, you're most likely already doing things like sessionizing the data. So taking the raw data and kind of aggregating it by sessions. You're probably already cleaning your data, cleansing it. And so that's another example of you're creating a materialization of data that's a little bit closer to what the users are going to be interested in, or at least closer than the actual raw data. You may be creating data that's partitioned by the region or the time, so that queries can run faster. So that's an example of materializing data that's again closer to what the user wants, or can enable queries to be much faster. Or maybe you have the data summarized for a specific kind of purpose. Now the challenge here is that today, by doing this, you're creating all these other copies of the data, and the user has to choose depending on their need. So you have to take your analysts and you have to train them to use a different table depending on the use case that they have. So if the analyst wants to do some arbitrary ad hoc query against the raw events, maybe they have to go against the raw data. But if they're looking at they're interested in session level information, maybe they can go against the sessionized data, right? If they want to query only for data in a specific region, maybe they want to look at specific kind of aggregations on data belonging to just one region or 1 year. Well, then using a data set that's already partitioned by region and time can be more effective, but the user, or the analyst, I should say, has to know what is the ideal materialization to use. And as they're going through an analysis journey, they have to be able to understand that the data set, the optimal data set for each query may be different. So they kind of have to go in and out from different data sets. So the benefits of having a relational cache compared to doing this kind of manual copy and pick type of an approach is that the cache is able to pick the best optimization to use. And so if you think about the approach with these data reflections, the user doesn't have to worry about these data reflections. The user's not even aware that these reflections exist. They're just querying the kind of the logical model, and the cache automatically picks the right optimization to use. In fact, the cache can also design and maintain these reflections. So these reflections really, that is what the relational cache contains. So just to summarize, a reflection is really a materialization that's designed to accelerate queries. It's transparent to data consumers. It's not required on day one. You can add any reflections at any time. And so that means you can get started with the system and do kind of ad hoc analysis within a minute of setting it up. And then reflections can be created over time to optimize various workloads, right? Very different from kind of traditional approaches to query acceleration like cubes, where you kind of spend weeks or months in advance kind of trying to figure out what questions are people going to ask, and how do I model that data and how do I create these cubes. In this approach here, with reflections, none of that is needed. You can just get started, query any data at any time, and the reflections kind of kick in behind the scenes without having to kind of point your BI tool or your application at a specific materialization. And what's really important here is that one reflection can help accelerate queries on thousands of different virtual data sets. So the logical model here, the logical world, you may have thousands or hundreds of thousands of different data sets that users have created over time. That doesn't mean you need thousands of these reflections. You may have one reflection that's helping to accelerate queries on thousands of different data sets. And that's because ultimately most of the data in an organization is derived from a much smaller subset of kind of raw data sets. And so the system can understand the relational kind of algebra and the relational connections between all these different data sets and leverage these reflections in a more intelligent way, right? In a kind of a broader way. The reflections themselves are persisted, and so they do not require any memory overhead. They don't have to fit in memory. The system can utilize things like S3 or HDFS or local disks to accelerate those queries. A combination of columnar on disk and columnar in memory is utilized here. So columnar on disk, we utilize Parquet for the most part, and in memory, we utilize Arrow. And this technology is scalable. It can scale to thousands of nodes. It's entirely open source as well, so you can go to the website and just download it or go to GitHub and look at the source code. So let's talk a little bit about just two kind of different types of reflections based on how they're managed, how they're refreshed. And so the simplest type of reflection to use is the managed reflection. And the managed reflection is basically managed by Dremio in this case. Just for manageability reasons, a reflection is always associated with a specific physical or virtual data set. Again, it may accelerate queries on thousands of other data sets as well, but in order for users to be able to manage and find that reflection, they're always tied to a specific kind of data set. And then in connection with that data set that they're attached to, there are kind of two types of reflections that are very easy to create. One is a raw reflection, which is kind of the row level granularity reflection. The data is columnarized, very highly compressed, and then it can be sorted and partitioned and distributed in specific ways. And then you can have aggregation reflections as well tied to that data set. And aggregation reflections are basically reflections that are partially aggregated versions of that data set based on specific dimensions and measures. And again, they can be sorted, partitioned, and distributed as well. The managed reflections are always persisted as Parquet files on either S3, Azure Data Lake Store, HDFS, MapRFS, local disks, etc. So these are persistent columnar representations of that logical data. In the future, there will also be in-memory reflections based on Apache Arrow, and that will be great for data that's very frequently accessed, for example. And so here's an example when using the command line as opposed to the user interface on how to create a reflection. So you basically use kind of alter data set. This is the path to the data set that you're attaching the reflection to, and then you either create the raw reflection or the ag reflection. You can give it a name that makes it easy to then kind of track how it's being utilized and so forth. And so when it comes to aggregation reflections, you specify the dimensions and the measures. And when it comes to raw reflections, you're just specifying the columns or the fields that are included in that reflection. So you don't have to include all the fields in that data set. You may say, you know what, there are 300 fields in this data set. People are only going to be querying these 15 fields. So those are the ones you're going to have. And then it would be great to use the partitioning or the local sort kind of methods here in order to kind of designate specific fields that are often being used inside of filters, for example. Now, how these reflections, these managed reflections, get refreshed really depends on the data set size and the nature in which the data set, the raw data, is getting updated. And so there are multiple different strategies here for refreshing partitions. It starts with kind of the simplest one is the full refresh, where the reflection gets recreated from scratch on kind of a schedule, basically, or at some period of time to maintain a specific SLA. And so that's great for reflections or for creating reflections on data sets that are generally smaller, right, in the millions, maybe billions of data, and also when the data is highly mutating, right? It's sometimes it's just most efficient to recreate that reflection every time if the data is changing rapidly. For data sets, for example, that are very large and maybe append only in nature, and that's a very common kind of pattern that we see as event data or time series type data where you're never really changing the data, but you're adding tons and tons and tons of data. We can use kind of a more incremental approach there. And when it comes to files in a file system, basically the system can automatically identify new files in a directory, and based on that, incrementally updates these raw or aggregation reflections. Partition reflections are great when you have things like Hive partitions or data is organized in directories, and so there's a kind of a well-defined way of identifying new kind of buckets of data that are being added to that reflection. And then finally, incremental for kind of tables that have kind of smaller tables, maybe relational databases or NoSQL tables. We can also build the reflections incrementally based on a monotonically increasing field. So you may have like a last created or created at kind of a field, or just a primary key that's always increasing. Now, the alternative to this is what we call unmanaged reflections or external reflections, and you can utilize your own ETL pipeline, your own external tools to create reflections as well. And when you're using these external reflections, you can basically run, for example, a Spark job, your own Spark job that creates some materialization of data, and then you kind of register that materialization with the optimizer and say, this materialization is represented by this SQL query, and then the optimizer can use that as a reflection across the entire kind of logical space. So there's a lot to cover here in terms of managed reflections as well. One thing we didn't mention is there's a refresh order in which these reflections get refreshed, and so sometimes it's beneficial to, for example, first update the raw reflection, and then if there's an aggregation reflection as well, update that based on the raw reflection rather than utilizing the source data. What users are really defining is not so much just a schedule, but what we call freshness SLA, and so that's roughly similar to kind of the refresh frequency, but it's really designed to ensure that queries on data never return data that's older or more stale than a specific kind of defined SLA. And so the system automatically tries to figure out, okay, what's the right time to start updating the reflection? How should these reflection updates be ordered, and so forth, in the optimal way to achieve that kind of an SLA. I kind of mentioned briefly the unmanaged or external reflections, which are new actually in Dremio 1.5. And with unmanaged reflections, you can create and manage materializations on your own. So you can use Spark, or you can use ETL jobs, you can use scripts, but basically you're responsible for creating these reflections and refreshing them as needed. And so basically, you can create reflections in any data source that Dremio supports. And so Dremio supports not just file systems and data lakes, but even relational databases and NoSQL databases. So these reflections can live anywhere. And the key is that once you've created or refreshed the reflection, or actually just when you've created it, you can call a specific command, specific SQL statement here, to register that reflection with the optimizer. So basically, you do that by providing a SQL statement in the form of a virtual data set that defines what is that target, what does the reflection represent. So if you've used, say, Spark to create an aggregation based on a few dimensions and you have a few measures there, you simply provide that equivalent group by SQL statement as the definition of a virtual data set, and then you utilize this command to say, okay, this SQL statement represents that specific materializations that you've created through some external system. Okay, so let's look at an example here, and we'll look at a few examples of how the reflections get matched. So a lot of the algorithms here that make this work are about how do you take a specific query or a specific query plan, which is what happens after the query gets compiled, and match that to specific reflections. So let's look at what that looks like. So the first example here is an aggregation rollup. And in this case, we have the user's query plan. So this is what the user's SQL query got compiled to. You can see that it has a scan at the bottom, of table 1. It's then projecting two columns, A and C, and then aggregating by A and summing up the C column, and then finally filtering that column so that we're keeping only the records where C is less than 10. If you take that query plan here and we have a reflection in this case, which is a scan of T1 and an aggregation of A and B by A and B on top of that and summing C, what you can see here is that we can actually replace the aggregation we can replace the scan of T1 and part of the aggregation by utilizing this reflection. So you can see on the right hand side here we have scan of R1 instead of scan of T1. So we're actually not needing the raw data at all in this case. We're taking the reflection itself, aggregating by A, because the reflection itself was an aggregate by both A and B. And so we kind of need to aggregate again on A, and then finally apply that filter on top of that. And so what we were able to do here is take advantage of the reflection, which was most likely much, much smaller than the original table, than T1. Let's look at another example here where we're doing a join / aggregation transposition. And so in this example here we have a simple join. It's an inner join between two tables, T1 and T2. And then we're aggregating by A and summing C. And so in this case we have a reflection in the system that's a scan of T1 and an aggregation on the ID on the join key. And then again summing C. And so what we can do here is replace the scan of T1 with a scan of this specific reflection, which is aggregated already by the ID. And that's possible because the join key is that ID. And then again, we apply the aggregation on top of that. And so in this case, most likely R1 is much, much smaller than T1. That depends, of course, on the cardinality of the ID column. But this provides us with potentially a much lower cost query plan. Let's look at one other example here where we have a simple query. This is a scan of T1 and then a filter on a column called A. So we're filtering and keeping only the records where A is equal to 10. And in this case, we have two different reflections in the system that are logically the same. So they're both simply scans of T1. But in one case, it's a scan that's partitioned by A, and in one case, it's a scan that's partitioned by B. And so in this case, the optimizer automatically figures out that it can actually leverage the reflection which has the data in T1 partitioned by A and utilize that. Simply prune the partitions and keep only the partition where A is equal to 10. So that helps us look at a very, very small subset of the original data and provide a much faster response here. So this is another example here, something called we call Snowflake reflections. And so in this example here, we have a scan of the original query. The user's query is a scan of T1 aggregated by A, and we're summing C. And so we have a single reflection here, which is basically a join of T1 and T2, and it's what we call a non-expanding join, meaning the number of records is not changing as a result of the join. This is what you typically see with kind of a fact table and dimension tables, right? Where the dimension tables, joining the fact table with the dimension tables results in the same number of records that you had in the fact table. And so what we're able to do in this case is that even though the user's query is only on the T1 table, and the reflection itself was created on a join between T1 and T2, we can actually leverage this reflection to accelerate this query. And so you can see that we're able to utilize the reflection and then aggregate by A and sum C on top of that reflection, right? So this is really, really useful when you have these kind of Snowflake type of designs where you kind of have a fact table and then kind of many dimension tables kind of often joined to that fact table. So you can take that that big join that you have with all those different tables, create a reflection, whether an aggregation reflection or a raw reflection on that, and that can then help accelerate queries even when they're not querying that entire kind of join. Maybe they're only querying two tables out of those. So let's look at that example in more detail. So this is an example of a Snowflake reflection. So here we have a fact table and kind of dimension tables joined to that fact table. We also have another dimension table off of one of these dimension tables. And so when you have this kind of a join represented as a virtual data set, and then you define reflections associated with that, the reflection engine automatically determines that this join represents a snowflake, meaning it has kind of the fact table and all these dimensions, and it determines that based on the join expansion. So when this data is when this reflection is getting materialized, and the system is actually running this join for the creation of that reflection, it can see how are these joins behaving based on the actual data. So the user never has to say, this is a fact table, this is a dimension table. Somebody created a join between all these things, and the engine is smart enough to figure that out based on the fact that, just as a simple example, the number of records coming out of the join between the fact and one of these dimensions is the same number of records that were in the fact table. And so that means it's a non-expanding join. And when somebody queries data, that lets us match a broader set of queries here. So in this case, if somebody's querying just these 3 dimensions and the fact table, that query can get accelerated thanks to this Snowflake reflection. And also if somebody was querying just the fact table and these 2 dimension tables that you see in the green box here, that could also get accelerated. So the system's kind of intelligence around looking at understanding the data itself when reflections get created helps it then make these determinations that this reflection can be utilized for these types of queries. Because in some situations, if we weren't looking at the data, there could be joins where the join is actually kind of creating duplicate records, right? And then it would not make sense to utilize that kind of join, the reflection on that join for subset kind of joins like you see here. And what we've seen in kind of real world results generally with reflections, not just for snowflakes, is that many or actually virtually all organizations that utilize reflections are seeing anywhere from 10 to many orders of magnitude performance improvement in kind of in their real world kind of analytics environments. It's not just about speed, though. It also reduces the compute resources that you need to achieve the desired performance. And so when it comes to deploying in the cloud, that means potentially orders of magnitude lower bills, right? When it comes to how much resources you're needing, or potentially just being able to do more kind of round trips, more iterations on the data. And then it also results in a reduction in disk space, because you're now eliminating the need for all these hundreds of copies that people are creating today. Again, going back to that, having kind of a logical world for users to operate in, and having the relational cache utilize a much smaller footprint to provide just for the purpose of performance. Right? So that gives you a big cost saving as well. Let's dive into kind of a demonstration here. So what we're going to start with here is let's look at the system. Okay. Make sure I'm on the VPN here. Okay, great. So what we have here, actually, let me connect to a newer cluster. I'll grab the URL here on Slack. Oh, that's actually it. Okay, so what we have here is a single Dremio cluster. Right now it's only connected to 3 data sources. So we have kind of an HDFS cluster, we have Elasticsearch, MongoDB. You can connect to many different data sources. So Dremio actually supports over a dozen different sources of data. And you have the spaces here. These are spaces are a place where these virtual data sets live. So basically the area of the spaces here, that's where this logical world exists, where users are creating virtual data sets. And in fact, users can also create virtual data sets in their own personal space. So every user has their own personal space. So just as a simple example to get started here, let's look at some data. And so we have this data set here with New York City taxi trips. This data set has about 1 billion records, and it has all the New York City taxi trips from the last 5 years. So each record, or not the last 5 years, but some 5 years here. So each record here represents a single taxi trip. So you see the pickup time, the drop-off time, number of passengers, the trip distance, and so forth. This is a logical, a virtual data set. So nyctaxi.trips. That's kind of the canonical name for this virtual data set. And we make it really easy with a variety of different tools to kind of launch these tools on your desktop with a live connection to the Dremio cluster. And I'll show you what that looks like. So normally, a query on this data set, let's see, all this old stuff here. So normally, a query on this data set takes, if we were just querying the raw data without the help of reflections, would take us something like maybe 6 to 10 minutes using kind of a SQL engine on this data and on this size of cluster. But the reflections basically help us make this much faster. So we can look here at an example. Again, this is a query if run in Hive or kind of any other SQL engine would take us minutes. I can drag that here, and you can see that the response comes back in less than a second. So we've just counted 1.03 billion records, and I can group this by let's say the drop-off time and see, okay, when are taxi trips, what year, or how many taxi trips were there per year. And so you can see here we have about 170 million taxi trips every year. And if I wanted to look at other things like the tip amount maybe and put that in the color here, and let's change that to an average, you can see that everything here is fast, happening extremely fast. So all these response times are kind of sub-second response times. And what we're seeing is that the average tip amount has been going up from 2009 to 2014. That's because the economy has been getting better, I think. If I looked at it by month, I could see that if I wanted to be a taxi driver, it'd be better to do that later in the year than earlier in the year when the tips are lower at the beginning of the year. July seems like an anomaly. I can kind of drill down by day and so forth. So you can see all this response time for the queries that I'm running on this New York City taxi trips data set are extremely fast. If I go to the jobs screen here inside of Dremio, what I'll see here is this flame here. And so this flame basically is an indicator that these queries got accelerated. So you can see here that they got accelerated, and we even show here what reflection helped accelerate this data. So you can see there's actually a reflection not on that specific virtual data set, but on this other data set called trips with date that helped us accelerate this data. And I can actually open up this reflection and see, okay, what does that reflection look like? So this is a reflection actually that was created kind of attached to a data set that was derived from the taxi data set. It has, I think, some additional columns like the drop-off date. But you can see there are dimensions and measures here, and so it's kind of a partial aggregation on that data. It's consuming 79 megabytes as its footprint on this much larger data set. And so this is providing us with the ability to achieve much faster kind of response time on this data. So that's an example of reflections. Now, users can operate, again, in a logical world. So a user may take this trips data set and say, you know what, I want to, I'm not happy with this data. I want to, maybe I don't need the vendor ID, so I'm going to drop that. Maybe I only want to look at, maybe I want to rename passenger count to passenger num. And I can go ahead and save this data set as a new virtual data set, give it a new name. Maybe I'll put it in the same space called New York City Taxi, but I'll call it trips without vendor. And now this is a new virtual data set. There was no cost to creating this new copy of data. It's all logical. In fact, I can even see the definition of this data set. So I can see passenger count being renamed to passenger num, and you'll actually, I guess you won't see that, but you may notice that vendor ID is no longer in this. So we've kind of trimmed down we're projecting basically a subset of the columns. If I go and query this data set now from the BI tool, so if I go back to my BI tool, in this case Tableau, and I click on data source here, let's go to our space here, the New York City taxi space, and I can drag the trips without vendor, and I can start querying this data, and this will be just as fast. So you can see that just refreshed the query on this data set, and that was fast, even though that's a completely new kind of data set that's a different copy of the data. So let's look at the quarter here, and that's again a different query. You can see that it was able to aggregate based on the quarter extremely fast. And so if I go to the jobs, I can see these queries on the trips without vendor data set here. See, trips without vendor is the name of the data set. Again, it's being accelerated thanks to that same aggregation reflection that we were looking at earlier. So this is a very simple example of how reflections are providing orders of magnitude performance improvement. And again, it doesn't have to be, I was using one specific BI tool. You can use other tools like Click and Power BI um, and so forth. But I can also use just SQL queries or notebooks. So for my more technical users, they can go through the notebook here. So let's look at an example here. The first example here just uses PyODBC to connect. And so what we're doing here is that same query. We're looking at the average tip amount and counting the number of records from that New York City taxi trips data set. And we're grouping on the year. So we're using the SQL extract function to extract the year from the timestamp. We can also use pandas. So a lot of people in Python use pandas because that allows you more flexibility. So in this case, we're using pandas and we're calling the read SQL function here and basically getting kind of a table here with the year, the average tip amount, and the number of trips in that year. So you may remember kind of the 170 million number that we were looking at through Tableau. We're seeing the same thing here. Let's look at some simple examples here. We can kind of do an aggregation roll up here. This is, we're extracting the month, and so we're taking that data set and now looking at by month. So that was a simple example we also did in Tableau. Here what we're doing is we're actually looking at kind of raw data. So we're looking at the drop-off time, the passenger count, the total amount, so 3 columns from this New York City taxi trips data set, but we're not aggregating. So here we're just looking at, give me the records where the vendor ID equals VTS, and the date portion of the timestamp is, this is Christmas, I guess, 2010. And so if I run this, you can see that comes back extremely fast as well. So even though we have 1 billion records, I got a sub-second response time on a raw query, one that did not involve aggregating the data. And so you can see that these are, I limited it to 10 just for display purposes, but you can see that the drop-off time here, these are all passenger drop-offs that happened on the 25th of December in 2010. Number of passengers, the total amount. Let's change this to 2014 and do another query here. You can see that, again, comes back in less than a second. And if I go to the job screen here and scroll to the top, I can see these queries come in. And you can see this is the query that was just sent from the Jupyter Notebook. And again, why did this get accelerated? Why does this have a flame here that caused it to come back in less than a second? Well, let's just look at the accelerated by and see the reflection that was helping us accelerate this. So in this case, it's a raw reflection. And you can see it has all these different columns, but it's partitioned by the drop-off date. And so these queries, because they are filtering on the drop-off date, this specific reflection, the optimizer was able to identify that it could utilize this reflection and kind of look at a very, very small subset of the data and prune away the other partitions. So let's go back here. And the final example I have here is one of a Snowflake reflection. And so in this case, you can see what we're doing is we're doing a query. This is across 3 different tables. One of them is an Elasticsearch data set called Review. These are all the Yelp reviews. Another one is a data set inside of MongoDB with the businesses on Yelp, and then we have the users on Yelp. That's kind of the third one. It's a simple inner join across these 2. So Review, think of that as the fact table. Businesses and users are the dimension tables, and then we're grouping on city. So let's look at that. And we can see that comes back really fast. Let's look at why that came back fast. So again, we'll go to the job screen here. That's the easiest way to kind of figure that out. And you can see we have these 3 data sets. But why were we able to do that so fast? Well, we actually didn't have to do that join in real time in this case. We used this reflection called by business location and user cohort. It's a reflection associated with reflections.ereviews. So we had created this virtual data set. I happen to call it reflections.ereviews. So let's click on that. I'm using the kind of the built-in data catalog here. And you can see what this data set is basically a join between the business data set in Yelp, the review data set in Elasticsearch, the business data set in Mongo, review data set in Elastic, and the user data set inside of Mongo. And if I click on the gear icon here to see the settings, and I go to reflections, I can actually see, well, we don't have any raw reflections here, but we have two aggregation reflections. So we have one where we're aggregating this three-way join by city and by state and by Yelping since. So that's the user cohort. What month did the user join Yelp? And then we have some specific measures like the review stars and just also, of course, the number of records. And then we have a separate aggregation reflection. This one is by business ID, which is a higher cardinality column. So we didn't do this one along with the other dimensions in the same reflection. We have it as a separate dimension here. And then, again, we're using the measure as review stars. But this is a three-way join. And the query that we just ran through the notebook was actually on those three exact tables. And so that was kind of a relatively easy one for the optimizer to figure out, even though we're not referencing the virtual data set, which we could have. We could have just queried the virtual data set here and said, you know what, instead of doing this join here, you know, we could query, let's see what this data set was called, reflections.ereviews, right? So we could just query reflections.ereviews instead of querying the join. So that's if the user actually knew that virtual data set existed, they could do that and they'd get the same response. Okay, but that's not what we were doing. We were actually doing the join from the raw tables in the SQL itself, and the optimizer was smart enough to figure out that it could do a match there. And you know, the system knows how to deal with different orders of the joins and all sorts of different query structures. There's a lot of different algorithms here that help us do these kind of matches in a smart way. But where you see the Snowflake reflection technology really helping out here is, let's say the user only cared about reviews and businesses. So the user was looking at, you know, I want to see how many businesses there are per city, okay, and kind of sort them in descending order, and then show the top 10 businesses by, the top 10 cities by number of businesses, right? And so in this case, we're going to run that and see that comes back really fast, and we see that Las Vegas has the most businesses in this data set, followed by Phoenix and Scottsdale. But we didn't actually have a reflection for this specifically on this join. What's happening here in this case is that we're utilizing kind of the power of Snowflake reflections. And so let's see. Sorry, that's the wrong cluster. Let's go here to the job section, and we can see that this query that had just come in on these two data sets was accelerated using that exact same reflections. And so the system was smart enough to understand that this specific reflection, even though it was defined in association with a three-way join, one of those join tables, in this case mongo.yelp.user, could actually be ignored because it wasn't affecting the number of records in the reflection. It's basically a simple dimension table, and there's always a match. So that's an example of where reflection or Snowflake reflections are helping. So we've seen a bunch of different kind of examples of how the optimizer is able to leverage reflections and be smart enough to kind of substitute something in the original query plan with one of these reflections and increase the speed of the query by orders of magnitude. And the nice thing is the user never has to worry about it. So the user is always kind of operating on the logical data sets, right? The user goes in and they just play with the data. And there are all sorts of capabilities we haven't shown here, like being able to curate the data, do all sorts of transformations. So even non-technical users can go into a data set and say, you know what, let's say in this case it's a data set inside of MongoDB, but maybe I want to logically I want to drop the underscore ID column, and I want to look at a subset of the cities. So we provide all these visual tools to give the non-technical users also the ability to kind of curate data on their own. But again, all in a logical world. No copies are being created here. So even as the user goes in here and maybe they want to flatten this array of categories that we have for each business into one category per record. So the user does all these things. No copies are being created. Even when I go and save this new data set, and let's save it in my own personal space and call this categories, this is a virtual data set. That's why it's green here. And users can go and create hundreds or thousands of these data sets without any problem. Reflections are all about the performance. Virtual data sets are all about enabling users to curate data and look at data through different kind of lenses. So before we wrap up here, this was a talk at Strata, so people were able to drop by the booth. Feel free to reach out with any questions to myself, Tomer, or to Jacques, who's my co-founder. And I would encourage anybody to go to the GitHub page here for Dremio. You can look at the source code. You can also go to the Dremio website and download the technology already packaged, and you can go to the community website and ask questions and get responses from the community. And these are kind of the two Twitter aliases that you might want to follow. Thank you so much for joining.